Okay, I have prepared problem number 1 for the assignment. Ganymede, 32 days is the orbital period. We don't know the radius of the orbit. We want to find that out. Io, 1.8 days as the orbital period with a radius of 4.2 units. Third law, always put the unknown on top, so RG is in the numerator. So let's do what we have to do here. So TG is 32 days over 1.8, and that squared is equal to RG cubed. Now I'm going to have separate and cube each of those like so. Alright, so I say the cube root of 32 over 1.8 squared times 4.2 cubed is going to be the radius Ganymede. And when I put this in my calculator, let's see, let's pause a second while I get this. Okay, so I put this in my calculator and I got it at 29 units as the distance. Okay, pause again. Alright, for the second problem, we have an asteroid that has an orbital radius twice that of Earth. Now, Earth radius is commonly called 1 astronomic unit, 1 AU. So this would be 2 AU. And we don't know its period, so that's a question mark. The Earth period is 1 year. So using the second law, unknown on top, TA quantity over, that's 1 year, squared is 2 AU over 1 AU, and this is cubed. And then to get TA, we take the square root of the 2 cubed, and we get 2.8 years. And that's correct. Alright, pause. Alright, now this one is Venus. Venus average is 225 Earth days as orbital period. The radius for this orbital period orbit we don't know. Earth is 364 days at 1 AU. Now, since this is a constant, we can have any number of significant figures or digits that we need. So the third law, putting the unknown on top, RV over RE quantity cubed is equal to TV over TE quantity squared. So this is 1, this is RV, so that's cubed, this is squared, and the cube root on both sides says that the RV is equal to the cube root of this quantity squared, and so I wrote down 0.73, and then I remembered, okay, this has 3 sig figs, so I need to write 3 here, so 0.726 is what you should get. I don't think the back of the book has the correct answer on that one. Alright, for problem number 4, we have that Uranus has an orbital period of 84 years. And we want to know its mean radius from the Sun using Earth as a reference. So the period for the Earth is 1 year. The orbital radius for the Earth is 1 AU. So substituting third law, what you don't know, in the numerator. So RU over RE quantity cubed is TU over TE quantity squared. So we take the cube root of TU over TE, which is 84, quantity squared, take the cube root, and I get 19 AU. Alright. Okay. On number 5, Mars is 1.5 AU from the Sun, and Earth is 1 AU. They want to know the period of Mars, and the period of the Earth is 1 year. So use your third law, putting the unknown in the numerator, and so that's 1 and that's 1. So the period is the square root of 1.52 cubed, and so I've got 1.87 years for this problem. And of course it says here in days. Well, I didn't read that till just now, so just a second. So multiplying by 364.25, I get 683 days. I think the back of your book says 684, which I don't see how they got that. So let's prep the next problem. Okay, for this problem, the moon is orbiting the Earth, and we have this data. The satellite is orbiting the Earth, and we have this data. And we want to know what is the period of this satellite. So third law, period of the satellite over the period of the moon squared is equal to radius of the satellite or the radius of the moon. Those are orbits, of course. And we do our substitutions. TS over 27.3 days is equal to RS 6.7 E3 over 3.9 E5. Going cubed, solve for TS. It's going to be the square root of 27.3 times 6.7 E3 over 3.9 E5 cubed. Alright, pause and let's see what that's going to be. Okay, well, first of all, I missed that square right there because we're supposed to square both of those and then take the square root. So I ended up with 85.5, 88.519 minutes because I multiplied this answer by 1440 is minutes per day, and this was days, so that is minutes, so it's 89 minutes for the answer for this problem. Okay, one more problem. Well, there's a B part. This is A part. B part, how far above the Earth's surface is this satellite? Well, for B part, we take the radius, we take this orbital distance, which is RS. Okay, so you have to look at it like this. Here's the Earth, and our satellite is orbiting above the Earth, and everything is measured from the center. So this is satellite, and when I subtract RS minus the radius of the Earth, then I get the actual height above the Earth's surface. And we're using the Earth having a radius of let's see, Earth radius is on page 180, 6.38 E6, 6.38 E6 meters, which is 6.38 E3 kilometers. And then I subtract 6.7 minus 6.38, and I get that above the Earth is 0.32 E3 kilometers, which is 3.2 E5 meters. Or 3.2 E2 kilometers. All right. That's the answer for that one. Let's pause. Open. Open. I've got 1 divided by 27.3. Quantity squared. Times 2.9. Clear all that. Clear all of it. Clear, clear, clear. Open, open, open. Okay, it took a little bit of doing, but you follow this, do the cube root of all this, and 43015, and so that's 4.3 e to the 4th kilometers, and that's the correct answer for that problem. All right, we're done. I'll close this and talk to you later.